Okay, now we're going to quickly go through torques and couples. I'm going to talk about how we define a torque first. A torque is always associated with a force. It is the tendency of a force to cause a rotation of the body in which it acts. This tendency depends on the magnitude and direction of the force, and also on the location of the point where it acts. For example, it's easier to push a door open by its handle than near its hinge. In the diagram, F1 and F2 act on the body. Both forces act along lines that lie in the plane perpendicular to the axis. So here we have force F1, force F2, and there's the axis here, right in the middle here of this object. The forces, when we start to pull, if we pull this object in that direction, then the perpendicular distance, we're going to call that L2, and the perpendicular distance from F1, we'll call that L1. And these lengths here are called the moments of the torque, the moment arms of the torque. You know that a longer force, longer length, and you'll be able to move it more with a smaller force, etc. So that's giving you the sort of idea of torque. Now, if L1 equals 0, there is no tendency to cause rotation. So if this here, you can imagine that this distance here, if we were right on here, then there'd be no rotation. We'd be just like moving. We'd be translating it. There'd be no rotation at all as such. The role of the distance L1 then is analogous to that of a wrench handle. We can turn a tight bolt more easily by using a long-handled wrench than a short-handled one. The distance L1 is called the moment arm of force F1 about the axis through O. The product F1 L1 is called the torque or moment of the force about O, denoted by the Greek letter tau. Think of this as an axis through here, so we've got some kind of axis through here, a bar or something. So the moment of torque of a force about an axis is the product of the force and its moment arm. So that's its moment arm and that's its force, and there we have the general equation there. To distinguish between the directions of rotation, we will usually use the convention that counterclockwise torques are positive. So when we're going in this direction, we normally say that that's a positive torque, and clockwise torques, so when we're going in this direction, we say that's a negative torque. So for this torque, we will have 1 equals F1 L1, and the torque 2 for this force here will be minus F2 L2. So in SI units, where the unit of force is the Newton and the unit of length the meter, the unit of torque is the Newton meter. When a force F acts at a point P having a position vector r with respect to an origin O, as in this diagram, the torque tau of the force with respect to O is defined to be the vector quantity r cross F. Recalling the definition of the vector product, we note that the magnitude of torque is rf sine theta. So we can say then that r sine theta, so that gives us our perpendicular distance. So the magnitude of the torque is equal to F times L in agreement with our previous definition. The direction of torque is perpendicular to the plane of the figure, in this case into the plane, as determined by the right hand rule. So here we've got, as we said, R cross F. So if we cross R with F, it's perpendicular to the plane here. Now we're going to discuss couples. Sometimes the forces on a body include two forces of equal magnitude and opposite direction, with the lines of action that are parallel but do not coincide. Such a pair of forces is called a couple. A common example is a compass needle in the magnetic field as shown. So here we've got a compass needle and we've got a magnetic field that's going in this direction as shown. The north and south poles of the needle are acted on by equal forces, one toward the north and the other toward the south. Except when the needle points in the north-south direction, the two forces do not have the same line of action. So unless this compass is actually pointing in the north-south direction, we're going to have some torque involved. This diagram here shows a couple consisting of two forces, each of magnitude F, separated by a perpendicular distance L. So they've both got magnitude, they've both got the same force applied to them, and they're only separated by a distance L. Now the resultant of the forces, so if we calculate the forces, obviously the resultant force is F minus F, which is 0. So you know, when you add those forces together, you're going to get 0. The fact that the resultant force is 0 means the couple has no effect in producing translation as a whole of the body on which it acts. So this whole thing here is not going to be moved around in the plane in anywhere. The resultant torque of the couple is only to produce rotation. The resultant torque of the couple in this diagram, about an arbitrary point O, is, we can just say it's x2 times F1. Okay, so we've got it here, x2 times F. Yeah, so that's the torque, yeah, the distance x2 times F, minus x1 times F, because it's in the opposite direction. So if you just manipulate that out, you'll find that the x's cancel, and you're left with the origin, you know, the formula that we've seen before, that the torque is the arm times by the F. So the distance x1 and x2 do not appear in the result, and so we conclude that the torque of a couple is the same about all points in the plane of the forces. It is equal to the product of the magnitude of either force and the perpendicular distance between their lines of action. So, you know, because these forces are equal, then the torque is equal to just one of the, you know, we can just write down for one of the forces, okay, we can write down the distance between them times F. That defines the force, because if the forces weren't equal, we'd have translation going on. So an example of that is a plumber tightening a pipe fitting. He uses the principle of the couple. He applies a force to the end of the wrench handle and holds the pipe close to the fitting with the free hand, exerting an opposite force. Thus there is no force sideways on the pipe, which would put a strain on the opposite end, but only a torque tending to screw the parts together. So when the plumber screws his nut in, if it's if the nut is on a, maybe a pipe that can move around, he wants to keep that still. He doesn't want to move. He doesn't want that pipe that the bolt is being screwed on to move around anywhere. So he holds it with his hand and then gets the wrench and tightens it up that way. And with his other hand, he's putting an equal and opposite force which counterbalances this torque. Yeah. So that's what that's saying. So that's basically the concept of a couple. Okay, so let's first of all look at this diagram. What I've got here is this is some object here. Okay, and we've set an origin here. Now the force is acting on it. There's a somebody is like pulling this object up like this. Now in the process of going up in the air like this in this direction, that's actually causing the object to turn. So if we move back to the line of action of that force here and go all the way back so that we get this line here at right angles to this force, yeah, then obviously we've got that understanding of what a torque is when it's at a right angle, yeah. So we're going to move around, and we're looking at it at this point. We can see as this force is moved, we're going to get a tangential component of this force, which is going to go around in a, we could draw a circle, an imaginary circle around here, and that tangential component is going to move around that circle. So then what you do, that what I've done here is I've just defined the components of that force in the tangential direction and the radial direction that's going out this way. Okay, so that's everything that's saying in this direction. The distance between 0 and the point we've labelled as the vector r, and the arm of the lever, the arm of this lever here, that's going down here. This is the arm of the lever, and that's L equals r sine theta. So you can see that if we know what the angle of what theta is. There are three ways to calculate the torque of this force. One, find lever arm L and use torque equals FL. Two, determine the angle theta between the vectors r and f. Remember, the dot product, if we know the vector of r and the vector of f, we can find the angle between the vectors by using the dot product, so we can do that. The lever arm is then r sine theta, which is here. That's the lever arm. Torque then equals f r sine theta, FL, because we found L then. Right, 3, represent the force F in terms of a radial component. So this is the third way of doing it. Represent F in terms of a radial component F rad, which is this component here, along the direction of R. So that's along the direction of R. And a tangential component F tan, which is this component here, at right angles perpendicular to R. So I've sort of drawn a sort of ghost version here. It's at right angles. So that's really this component here, F sine theta, or F tan, as I've written it here. We call it tangential because if body rotates, then the point where force acts moves in a circle, which I've kind of just said, and this component is tangent to the circle. So, if this starts, when we move this force up in the air, this whole thing's going to rotate, and that component is tangential to the circle that will be made when this starts to move. So that's why it's called F tan. Then F tan equals F sine theta. So this F tan equals F sine theta, which you can see by this basically. So you can see that there is that there, so it's F sine theta, yeah. So that's that component, same as there, yeah. So you can get that from the angle. And torque then is equal to r, the distance r, times F sine theta, which equals the F tan times the distance r. So that's what you can get there. The component F rad, this component here, produces no torque. When we're doing it this way, it produces no torque with respect to O, because its lever arm with respect to that point is 0. Because it's going out that way, then obviously there's no distance L here between. There is no distance. If that was over a bit, then there'd be a distance. So that's why it's 0. Yeah? So the only component that's relevant here is this one. So summarizing these three expressions for torque, we have torque equals force times L, this distance, or R equals, we can define L as R sine theta, so RF sine theta. Or we can define the tangent component here and say F tan R. Okay, so we can define it that way, or we can define it that way. So now the other thing, looking at this one here, RF sine theta. Okay, so RF sine theta, which is this one here, is also magnitude of a vector cross product R cross F. Hence, the vector torque equals R vector cross F vector. This is known as a torque vector, yeah? So we can define the torque vector now, and that's what that is. Now, the torque is the magnitude of that, because obviously we know that the magnitude of this is this. So then we can just say that if we find this torque vector, then the magnitude of the torque vector is the torque itself. So, and also the interesting is the direction of torque is worked out using the right hand rule perpendicular to both R and F, and we've got R, the vector R. So if we're going to cross R with F, then obviously in this particular case we're going that way, so we're coming out of the page. So that's torque as a vector, and that's a useful general way of calculating torques. If when you're in 3D space and you've got all the components of the vector, you can use this torque vector to work out the actual torque. So that's a useful tool, something we might use later on.